Welcome everyone. This is a presentation on temperature effects of the laser diodes, an audio-visual presentation by Nirupam Deka and Manjil Gogoi, B.Tech, Electronics and Communication Engineering Department, Assam Bosco University, 2015. Introduction. This presentation discusses the effect of temperature on laser diodes in two phases. In first phase, we discuss an important factor to consider in the application of laser diodes is the temperature dependence of the threshold current. This threshold current increases the temperature in all types of semiconductor lasers because of various temperature dependent factors. The second phase is focused on an examination of degradation dependency of a semiconductor laser on a temperature of an LD package. Thermal conditions dependence and emitter optical power, spectral component which is emitted by the laser, electrical to optical power conversion, efficiency and many other parameters. The criticality of the parasitic parameters is evaluated in this paper. These parasitic parameters must be considered carefully to eliminate them efficiently. Now the threshold current. The complexity of various temperature dependent factors prevents the formulation of the single equations that holds for all devices and temperature ranges. However, the temperature variations of threshold current can be approximated by the empirical expressions. ITH, that is threshold current, is equal to IZ E to the power T by T naught, where T naught is the measure of threshold temperature coefficients and Iz is a constant. For a conventional strip geometry gallium aluminum arsenide laser diode, T naught is typically 120 degree to 165 degree centigrade in the vicinity of a room temperature. An example of laser diodes with T naught is equal to 135 degree centigrade and Iz is equal to 52 milliampere is shown in figure 1. The variation in threshold current with temperature is 0.8% per degree centigrade as is shown in figure 2. Smaller dependence of threshold current on temperature have been demonstrated for gallium aluminum arsenide quantum well heterostructure lasers. This is a current versus optical power graph, and this is temperature versus normalized threshold current graph. Now the temperature dependence. For these lasers, T naught can be as high as 437 degrees centigrade. The temperature dependence of threshold current for this device is also shown in figure 2. The threshold variations for a particular laser type is 0.23% per degree centigrade. For the laser diode shown in figure 1, the threshold current increases by a factor of about 1.4 between 20 and 60 degrees centigrade. In addition, the lasing threshold can change as the laser ages. Consequently, if a constant optical output power levels is to be maintained as the temperature of the laser changes or as the laser ages, it is necessary to adjust the DC bias current level. One possible method for achieving this automatically is an optical feedback scheme. Now the temperature control. Optical feedback can be carried out by using a photodetector either to sense the variation in optical power emitted from the rear facet of the laser or to top up and monitor a small portions of the fiber coupled power emitted from the front facet. The photodetector compares the optical power output with a reference level and adjusts the DC bias current level automatically to maintain a constant peak light output relative to the reference. The photodetector used must have a stable long-term responsivity that remains constant over a wide temperature range. For operations in the 800 to 900 nanometer region, a silicon pin photodiode generally exhibits these characteristics.
This is phase 2. The thin area of energy pumping when the rapid transmission from a spontaneous emission mode to a simulated emission mode occurs is called the threshold. A semiconductor laser is related with a term of threshold density of a driving current of threshold current. When the laser diode operating mode is changed from incoherent to laser, increasing temperature introduces decreasing of the features of laser diode. While the temperature increases, the ratio between the electrical power and the optical power decreases. The temperature also depends on emitted wavelength of the device operating life. Characteristic temperature. The parameter which determines the feature degradation of the laser diode is called the characteristic temperature T0. The characteristic temperature T0 can be derived from LI dependency. The LI dependency must be measured for two different temperatures, indoor temperature of 25 degrees centigrade and high temperature of 85 degrees centigrade. It is examined experimentally that there is an exponential dependency between threshold current and the temperature. Increasing temperature introduces an increase of threshold current. Characteristic temperature can be evaluated according to this facet as T0 equal to TU minus TD divided by log of E base of ITH TU divided by ITH TD, where TU determines high temperature, TD determines base or low temperature, ITH TU determines high temperature threshold current, and ITH TD determines base low temperature threshold current. The characteristic temperature T0 denote the measure of TTH, dependency on the temperature variations. The more T0 is higher, the lower temperature dependency is. Figure 1, which is below, shows the LI graph measured for different temperatures. The characteristic temperature can be computed from the formula 1. The required values of threshold current can be read from figure 1. These values are approximately 18 milliampere at the temperature 25 degrees centigrade and 41 milliamperes at 85 degrees centigrade. Thus, the characteristic temperature is 72.8 degrees centigrade for laser diode RLD 78 NPA. The standard temperature interval is from 50 to 75 degrees centigrade. These values of the characteristic temperature are used in telecommunication optical links. This is a LI dependency curve. This shows the derived current dependency of optical power, where temperature is the parameter. Slope efficiency ETAF. It is necessary to use a laser diode with the lowest value of threshold current, but it is also desirable to affect the emitted optical intensity by an increase of the current. In facet, this dependency is given by the rate of intensity rise, which is called the ETAF. Slope efficiency, differential sensitivity or differential efficiency of the laser diode. If a laser diode is used in telecommunication, some conditions must be considered. For example, if the current change is 10 milliamperes, the change of emitted optical intensity is approximately 1 milliwatt. The ratio of these changes is called ETAF and is defined as ETAF equal to dP by di. The theoretical LI dependency is linear in the area over threshold current, but in the real dependency there is some degree of non-linearity, especially in the area of saturation. As it was defined above, parameters of laser diodes get worse with increasing temperature. This facet is given by an activation of radiationless process in a semiconductor. Then a portion of the emitted light is converted to heat energy. Thus, the temperature effect on ETAF is following. Differential sensitivity of the laser diode is going down with the increase of temperature. In the other words, if the current is constant and the temperature is increasing, then the optical power is getting down. Laser diodes which are used in telecommunications are characterized by ETAF lying in the interval of 100 to 400 milliwatt per ampere. This is a graph which shows the variations of ETAF with respect to temperature. Now, spectrum deficiency. The spectrum is a set of wavelengths which is emitted by a laser diode in comparison to an LED. The spectrum of a laser diode is very narrow, which is from 0.1 to 1 nanometer. A typical spectrum of a laser diode with a Fabry-Perot resonator contains several longitudinal modes. The material and the length of the Fabry-Perot resonator determine the longitudinal mode wavelength. Laser diode spectrum dependency on a temperature. Increasing temperature introduces spectral shift to the higher part of the spectrum. This phenomenon is called longitudinal mode drift. The forward diode current affects the laser diode spectrum. Increasing forward diode current increases Joule heat and the laser diode chip temperature goes up. The forward diode current variations causes energy shift among the longitudinal modes. This leads to discrete hops of wavelength of the main peak. This phenomenon is called mode hopping. Laser diodes using Fabry-Perot introduces this phenomenon. Negative factor elimination. Integrated monitoring photodiode, usually pin diode, is used for constant optical power control in semiconductor lasers. This photodiode measures the instantaneous optical power. The instantaneous optical power induces a current in the photodiode. The feedback must be introduced. According to this, the supply current of the laser diode can be controlled and the constant optical power can be set up. Different type of devices can be utilized. Temperature stabilization must be applied to reduce the differential sensitivity and the main stability of the wavelength. The heat exchanger and Peltier elements are usually utilized. In these presentations, there was shown the important differences of laser features on temperature. The temperature can have negative effects on the important parameters and quality of semiconductor laser diodes. There is a need to know the dependency of parameters on the temperature for successful diode construction. Thus, the decent attention must be paid to thermodynamic conditions. It is required that a laser diode can work at low constant temperature. For this purpose, Peltier element with current sources is used. Electronics which is used with Peltier element can work duplex. Then Peltier element can work as a cooler or heating pump. Then the temperature of the laser diode is constant. With this the presentation concludes. Thank you.